In our previous video, we discussed the cylindrical coordinate system in triple integrals. Now, this system was actually the standard polar system used in space with the addition of the z coordinate, which came from Cartesian system. So it was not a system, in some sense, particular to 3 dimensions. It was just a maybe forced extension of the polars. Now, the coordinate system we will discuss now is quite genuine to 3-dimensional space. You cannot restrict it to 2 dimensions. It will just become polars in that sense. Okay. This is called the spherical coordinate system. Well, as in the cylindrical coordinate system or in the Cartesian system, in this system we have 3 variables. Now, these variables are the following ones. Okay. Now, given a point, say x, y, z, in space, okay, project vertically on the xy plane, then, of course, we can define the standard theta angle here. That's the polar angle. Actually, it's the cylindrical angle. Okay? But when you project, it becomes the polar angle as we know it. Now, instead of using r from origin up to this projection, we use here the distance rho. Let me use some colored chalk here. Would be better. Okay. Now the distance is from the origin to the point. Of course, this was r in the polar system, but this is different. And finally, we measure the angle from the positive z-axis. Call it the angle phi. So this system of 3 variables, rho, phi, and theta, is called the spherical coordinate system. So rho is the distance, okay, from 0, 0, 0 to the point P. Okay. So clearly, the distance squared is given by x squared, y squared, z squared added together. Okay. Now, theta, okay, is the angle, okay, in the projection starting with the positive x-axis. Well, you can, of course, lift it, okay, and consider this angle at the top. Okay. So it will be the angle which is measured horizontally parallel to the xy system. Okay. So it would be something like this at the stage. And so this would be, again, your theta angle. Theta is the angle measured from then the plane, the zx plane, okay, to the point. So this is the usual polar theta. Now, phi is the angle measured from the positive z-axis to the point. This will be best understood if we look at what happens if one of these is constant, as we had discussed before in cylindrical, polar, or Cartesian systems. So, when rho is rho 0, okay, clearly what we get from here is a sphere. Rho 0, hence the name spherical coordinates. It comes from here. Now, if phi is constant, okay, what do we get? Well, if you consider all points so that when you connect them to the origin, the angle from the z-axis, from the positive z-axis to this line segment is constant. It means that you take this line segment and you rotate that. Okay. Phi will be the same for all such points. Of course, the distance is not important. Okay. If you increase the distance and still rotate about the z-axis, okay, phi will still be the same, which means that it's a cone. So, when phi is phi 0, one gets, okay, a cone, but you have to be careful with the following. Phi is measured from the positive z-axis, and therefore, okay, one gets an upper cone. Okay, for phi 0 between 0 and pi over 2. Clearly, when phi 0 is pi over 2, that is, you have a cone, but you expand it until the angle is pi over 2, so what you get is the xy coordinate plane. So the plane, the xy coordinate plane, is actually a cone, a degenerate cone. Okay. And okay, a lower cone for phi 0 between pi over 2 and pi. Okay. So these arguments also determine the boundaries of these variables. Clearly, in the first case, I didn't mention that. Maybe we should say that rho is positive, but it can go up to infinity. But phi is between 0 and pi. Okay. And for theta, we have the obvious picture. Namely, if theta is constant, then one gets, okay, a vertical half plane. Okay. Namely, this one. Okay. But you have the bottom part as well. So it's a vertical plane, okay, with the angle theta 0. It's half plane because you measure it from the positive x-axis, as in this cylindrical system. Okay. So these constant values give us a sphere, a half cone, okay, with the degenerate case, pi over 2, and a vertical half plane. Now, a good question would be, do these three numbers, that is, if we fix a theta, a rho, and a phi, do they determine a single point? Clearly, the opposite question is well defined. That is, if we have a point, we can define these three numbers, rho, phi, and theta, as in the picture. Okay. But if we are given three such numbers, does that determine a single point? Well, we can argue as follows. Okay, let us first, okay, given a rho and a phi in the first place, what do we get? Well, rho, that is a given number, it means that we have a sphere. So we have a sphere here, okay, with radius rho. And phi is given, means that we have, I take a positive phi here, we have a cone. Now, if these two are fixed, it means that we have the intersection of the two. Well, the intersection of the two gives us clearly such a circle. It's a horizontal circle. Okay. Well, the picture is not that good, so let me modify it a little bit so that it looks better. Okay. So we have this circle. It is a horizontal circle. Now, on this horizontal circle hanging somewhere here, somewhere in the air, okay, determining theta gives us a single point, because determining theta means we intersect this with a vertical half plane. Okay, then intersecting this circle with a half plane, that means theta is theta 0, okay, we get a single point. In other words, okay, this argument shows us that rho, phi, and theta given, okay, when we intersect all those three geometric figures, we get a single point. Conversely, every single point determines a rho, phi, and theta. And so, this is a coordinate system. Okay. Okay. Converse is obvious. So, rho theta, okay, let me say rho phi theta, we will usually use it in this order, determines a single in space. So, it is a coordinate system. We can represent all points this way. Okay. Now, maybe a question could be the following. Well, why don't we have the values of phi ranging from 0 to 2 pi? It's an angle after all. And instead of that, from 0 to pi. Well, the idea here, the explanation, is the following. In here, okay, if we make this angle large enough so that we have pi over 2, okay, we have the xy plane. If we increase it further to pi, okay, we get everything up to here. Now, if we assign phi an angle larger than pi, it means that we would go around and stop at such a point. Okay, this is phi bigger than pi. So let me say maybe phi 0 bigger than pi. Well, this, of course, can be characterized by the other angle. Okay? Starting from z-axis, going up to here. Okay. And so, for such a point, we would have two phi values, which means that it will not be a coordinate system. Phi needs to be unique. So, we don't use this. Instead, we use this one. So, the angle phi is restricted to the interval 0, pi. It will not be greater than pi. Okay. And a last comment, when phi 0 is equal to pi, okay, what we get is the lower z-axis only. Okay, it's again a degenerate cone, a degenerate lower cone. Now, two examples, we illustrate this a little bit. Maybe before examples, I should comment more on this, namely some identities. Okay, regarding spherical coordinates. Okay, these will be practical, and we will be using them over and over again. Let me redraw the picture first. We have our point, that is x, y, z. We draw a perpendicular, okay, and consider, okay, this angle, which was theta, and of course, this length would be r as a length. And we have rho here, and here we have phi. So these three things characterize our point. Now we already noticed that rho square is x squared y squared z squared, because it's a sphere. Okay. The distance from the origin is constant, so we get a sphere in that sense. Now, what about r? Well, we want to express r using rho, so I can just look at what happens at the top. This is also r. Okay, if I go vertically up. So, r divided by rho, okay, gives me sine phi. Okay. Now, similarly, this would be my z, okay, and z divided by rho gives me cosine phi. Now, what about x? Well, we already know, because theta is polar theta, x is r cosine theta. But r was rho sine phi, so it is rho sine phi cosine theta. Similarly, y was r sine theta, so it is rho sine phi sine theta. So these identities okay? And this one, okay? They convert the Cartesian system to spherical coordinates. Okay, but this is also important because we know a lot of things about the polar system, and we will be using them in geometrical considerations, and we will see that it will be quite useful. So it's good to remember that R is rho sine phi. Okay. Well, using these, you can look at from the other side. For example, what is rho? Okay. Well, rho is the square root of these things. That's obvious. What is phi? Well, phi is arc cosine of z over rho. Okay. And instead of rho, if you write the square root here, you will have a formula showing phi in terms of Cartesian system. We will not be using them too often, and they're not very useful in practice, so I will not write them directly, but obviously one can obtain them. Similarly for theta, for example, okay, theta, where is my theta? Okay, it's here, it's arc cosine of x over r. We know what r is, we know what x is, and it just tells us, well, x is x. We know what r is in terms of x and y, and you can just get the identities from there. Okay. Now let us do some computations to get acquainted with the spherical coordinate system. Well, the first one is find the spherical coordinates of the point, say 1, 1, 1. Okay. Well, this means finding rho. Okay. Clearly, rho would be, because of the identity up there, the square root of x squared, y squared, and z squared. So it is root 3. Okay. Well, what is phi? Well, what do we know about phi? Well, phi is, or rather cosine phi is z over rho. Because z was rho cosine phi. This says that it is z divided by square root of 3. So phi is arc cosine of 1 over root 3. Okay, you can find the angle value. I will not go into that. Well, what is theta? Well, you can find theta directly from above. That's to say, theta would be, for example, say r is what? Rho sine phi. Okay. And it is, no, I don't want that. What do I want? Okay, let me use some polars here. Okay, that's much easier. Namely, y is r sine theta. Okay, so sine theta gives us y over r. Okay, y is 1. It's already given here. And r is the sum of the squares here, so it's root 2. Now this tells us that theta is pi over 4, okay, because sine is 1 over root 2. Okay. But it can also be 3 pi over 4. Well, this tells us that we have two cones here, two half cones. One is less than pi over 2, the other one is bigger than pi over 2. So this is an upper cone, this is a lower cone. Okay, thus, okay, we have the following. We have a cone here, okay, with angle pi over 3. But we have both sides, okay, because we have two pieces here. Now, as a second example, let us express a cone actually. So we will see it here. Okay. Express the cone x squared plus y squared is z squared over 3. Okay. In spherical system. Well, what do we have here? Let us use our polar knowledge a little bit. So we have x squared plus y squared is 1/3 z squared. Now this is r squared, the polar r, okay? And the polar r was rho sine phi in spherical system. On the other hand, z was rho cosine phi squared. Okay. So we get from here that rho square sine square phi, that is r square, is 1/3 rho square cosine square phi. Of course, this tells us that rho's cancel out. If rho is 0, well, it gives us, it will be given us by phi values anyway. So this simply says that tangent phi in absolute value is 1/√3. Okay. Now, of course, you can write this obviously in this form if you are not familiar with these values. So sine of phi is 1/2. The other one is the cosine of it is √3/2. So this says that phi is pi over 6. Okay. If positive. Okay. But it can as well be negative. So it can be what? Pi over 6, or it can be pi minus pi over 6. Okay. Clearly, one gives, okay, the upper cone as before, and the other gives the lower cone. Okay, this is bigger than pi over 2. So it's a cone. Okay, a cone where the angle is pi over 6 or pi minus pi over 6. Okay. Well, in short, this Cartesian equation is in a spherical system, nothing but a cone, and phi is pi over 6, or the lower part included as well. It's a complete cone in this sense. Now, to use spherical system, in triple integrals, as we did in cylindrical system or in polars, we need to determine, well, since we are talking about triple integrals in cylindrical system, okay, we need to determine the volume element. That is the differential volume element. okay, this means the volume of the solid, okay, where, okay, it's determined by, okay, or let me say which is determined by delta theta, delta phi, delta rho in spherical system. Now, if you change theta from some value by delta theta, and similarly for phi, and similarly for rho, of course, you get a solid piece, a very small piece, if these are small, in 3 systems. Okay. Now, to draw such a figure and to obtain something geometrically, okay, because it's too difficult for me to sketch it, I will just borrow it from the internet. Okay. Now we consider this picture on the right. Okay, there it's depicted. Okay, what we get roughly when we increase theta, phi, and rho a little bit. In the Cartesian system, it is shown in the Cartesian system. As you see, it looks like, well, a piece, but it looks like a rectangular box in some sense. And so, its volume, okay, will be the product of the lengths, almost the lengths of the sides, which, of course, would be the following. So, delta V would be roughly, okay, well, the part coming from delta theta would be R delta theta. In the picture, it's shown as D theta, but you can assume it's a little bit approximation. And R here is rho sine phi times, okay, we have the part coming from delta phi. Now, this delta phi is an angle, okay, where rho is constant. And when rho is constant, actually we have a sphere, but when phi is a fixed angle, it's an angle in a circle with radius rho. So the second part is rho delta phi. Okay. And finally, the length coming from changing rho is just delta rho. So it becomes, okay, as we see, rho square sine phi, okay, times delta theta, delta phi, delta rho, as we want it. This is the volume in the spherical system of a rectangular box. So the factor in this change of variable is this one. So this is, this should be the Jacobian. And this is the coordinate system in, usually we write it in this order, so let me write it this way. It's the volume of a rectangular box in the new system, and this is the constant which comes to the front. Now, in the picture, we see how these are shown. Now, even though we determined geometrically the volume or the differential volume element in spherical system, okay, and we remarked that it should be the Jacobian, okay, as in all coordinate transformations in multivariables or even a single variable, these are the Jacobian determinant in absolute value all the time. So let us check it directly this way, okay, as well. So, since, okay, the factor in change of variable of course in a triple integral okay, from Cartesian to spherical, okay, must be okay, the absolute value of x, y, z with respect to rho, phi, theta. Okay. Remember, this was the determinant, the determinant of the derivatives. Okay. So this is the absolute value. Okay. So this is the absolute value of the determinant. Maybe I can directly, okay, let me show it this way. The determinant of, okay, x with respect to the derivative of x with respect to rho, phi, and theta, of y with respect to rho, phi, and theta, and z with respect to rho, phi, and theta in absolute value. So let us calculate this. This is the absolute value of then, okay. Well, remember, maybe I should just remind you of that shortly. X was rho sine phi cosine theta. Y was rho sine phi sine theta. And Z was rho cosine phi. So, using them, let us take these derivatives. We have sine phi, okay, and cosine theta, derivative with respect to rho. With respect to phi, it should be rho cosine phi cosine theta. With respect to theta, it would be minus rho sine phi sine theta. Now the second one, we would obtain sine phi and sine theta. With respect to phi, rho cosine phi sine theta. And with respect to theta, that should be rho sine phi cosine theta. For z, it should be cosine phi. And then with respect to phi, minus rho sine phi. And with respect to theta, we have no thetas there. Okay. So this is the determinant we need to calculate. Let me do it in detail. Now I can erase this part. Okay. Okay. Now let me repeat. Sine phi cosine theta, rho cosine phi cosine theta, minus rho sine phi sine theta, and sine phi sine theta, rho cosine phi sine theta, and rho sine phi cosine theta. Okay. Now we need to calculate these products. Okay. Okay, looking at the diagonals, we obtain these calculations in absolute value. Of course, these minuses make everything plus. Now, if we write rho squared sine phi times what remains inside, we have sine square phi, sine square theta, plus cosine square phi, cosine square theta, plus, okay, cosine square phi, sine square theta, and again plus sine square phi, cosine square phi. Okay. Now, combining, of course, some of these, we have sine square phi, sine square theta, and wait a minute, this is theta, of course. And combining these two, okay, sine square plus cosine square is 1. So we get from here, okay, just sine square phi from these two. And from these two, we obtain cosine square phi. The other ones add to 1. So it is rho squared sine phi as expected. Okay. Of course, here we don't need to put any absolute value here because sine phi is positive. Namely, this is positive since phi is between 0 and pi. Okay. So we don't have to put absolute values. This is the Jacobian, which is the factor which comes into the picture.